Okay, hello students. So, any doubt from lectures 25, 26, 27? Okay. The route stability criteria I'm going to actually discuss about today in the tomorrow's video lecture that I'm going to post. Okay, so some questions related to stability. For that, you have to wait basically, So today, what I mean is today I will record it, and tomorrow morning I will post it. So the next 2 days, mostly today, I'm going to do that. Okay. So this is in your course, but since this chapter is a little bit bigger chapter, the content wise, so hence I already gave the tutorial problem, but doesn't mean that you have to solve it based on the last 3 lectures. No. Okay. So for route, please wait. Okay. So I'm going to discuss about it. Okay. Next. Okay. First question, second part, and 26th question. How will we approach other than Laplace inverse, because it is getting very long? First question, second part, and 26th question. First question, second part. Just a minute. And 26th question, just a minute. Okay, so the second part of the 26th question. So there is no way than a Laplace inverse Laplace transform, because Laplace transform method is actually the fast method basically. So when the second part, when you have in this similar to the when you have T and then RT is a line basically, right? With it says T equal to, this is RT, right? So RT equal to, and what it says 10 per minute, yeah? So you can say 10T, where T degree Celsius, right? That equal to degree Celsius, where T is in minute, right? So this is the how this one is. So, and you know that when you take the Laplace transform of that, RT equal to Rs, which will be equal to 10, and then you have T, so this becomes 1 over S square, or 10 over S square. Yeah. So the faster method, it is taking too long. Well, too long means not that too long, I think. Yeah. So this is the first order system. So let us say first you have to.
Sir, for 26, sir, for question it's taking long time.
Okay, 26 taking too long.
Yes, sir.
Okay, so you are fine with the first one now.
Yes, sir. I only needed to understand the concept in first one, second part.
Yeah. Okay. So is it okay now so far?
Yes, sir.
Yeah. Okay. So the first part is actually easy. It's not difficult. You have to. Main thing is how to write that in terms of 1 over some, you know, you have to break it into terms so that you can take Laplace inverse Laplace transform. You can accordingly you can change it. Okay, sir. Regarding 26, let me see. Okay, first of all, 26 is the second part when it is talking about a steady state error. You know, the steady state error, I'm going to tell the fast method in today's lecture. I mean the one which I'm going to record today or tomorrow. Yeah. So in a way, steady state error is not complete yet. You know. So basically there is a fast way of getting the steady state error. Yeah. So I will not answer that. The Define the open loop transfer function. Okay. So open loop transfer function, did you get? Okay. So regarding 26, so did you get the open loop transfer function, Aditi?
Yes, sir. Yes, sir.
Okay. So the steady state error, that is the way like we have studied so far in last 3 lectures, that you don't have to apply here. So don't take the inverse Laplace transform. Okay. So there is a faster way of doing it, which is based on the transfer function itself. Okay. So this is a much faster way. So that I will discuss. Okay. Either today or tomorrow. Okay. The one which I'm going to record. Okay. So next 2 video lectures, you will see that how to approach those. So sorry about that. I think there is some confusion. I should have written that few questions, for few questions you have to wait basically. Yeah. But you understand now that it's going that way, you know, changing to time domain, it takes a lot of time basically. So yeah, but okay. So for few questions we have to wait until like next 2 video lectures. Okay, then we can discuss about it. Okay, so next one is a tutorial assignment. There were questions to find rise time, peak time, etc. and value of B is given to be very, very small. So can we take B as 0 or tending to 0? Okay. First of all, I'm not going to discuss about the assignment part. You know, assignment you have to, few people have already done. So I'm not going to encourage that. So assignment question, uh, whatever assumption you want, you just take assumption and see. Both assumption you try, see how what do you get. That's what I can do. Not more than that. Okay. Okay. So I don't want to encourage students asking questions, because all those questions, if you really solve it, you will not ask those questions. You know. So wherever you have a problem, either we have to assume this and that, just try both of them and just see whether any change in answer is the same thing or like that. Okay. So not now. Okay. You have to try. Okay. Other than okay, so basically the uh, for all the things, the terms whatever I have used in the video lectures will be valid. So in the video lecture, if I have given rise time for a step input, it should be for a step input. If it is for something else, it should be for something else. That's what I can say. The idea here is to encourage you guys to actually look at the video lectures, and from there you can find out what I'm talking about. It will make sense automatically. So in any confusion, whatever is covered in the lecture is the one I'm asking. Yeah. Okay. So did it answer, Aditi? Okay. Now the B52, rise time, peak time are coming infinity. Please solve it once. B52. Just a minute. B52, let us see. How will it come infinity? First, tell me first. Ashutosh, how do you get infinity?
Sir, I just splitted the terms 1 over s and 1 over s plus 1 by s plus 1 minus s, and then took the inverse Laplace transform.
No, so see, that's the thing. Okay, man, please don't be offended if I tell you that you have probably not watched the the video lectures properly. Because this is open loop transfer function. So what you have to do is for the control, for the closed loop. Yeah. What it says, consider the unit step response of a unity feedback control system. Unity feedback control system means it is talking about the closed loop system. Okay. So what you have tried based on open loop transfer function, but you have to try with unity feedback control system, means you have to close the loop. Yeah. So what you have to do is see GS equal to 1 over S plus 1. See here. So goes like this one. Yeah. So what it tells you is when it says unity feedback control system, feedback, so it has a feedback. Remember, but this is unity means it has only one. So it goes like this one. Okay, so minus here plus. Okay. Now you find out the closed loop transfer function. So Ts will be Gs divided by 1 plus Gs. So open loop transfer function will be this time this only. So now you get whatever you get is S plus 1, 1 plus S plus 1. So what you get? 1 over S plus 1 plus 1. So 1 over S square plus S plus 1. Yeah. Now if you solve it, this one, this is TS, now you can do it. So this TS, now based on that, you got it like that. Will you be able to do it now, Ashutosh?
Yes, sir, got it.
Yeah, okay. So basically what you have to do is always look for whether it's a feedback control system or not. When open loop is given, that really means if there is a HS here, right? So let us say this is HS here, and open loop is given, that means GS times HS is given, is equal to 1 over S plus 1, and then your HS is 1, unity. So GS will be equal to 1 over S plus 1. Yeah. So once you get that, you can find out now. Yeah. Okay. Any other question?
Sir, from lecture number 27, in the last
Yeah.
you solved for the unstable system, second order with mass and spring system.
Okay.
So for that, you got x t is equals to 1 upon m into epsilon to power minus iota omega nt plus exponential iota omega nt. So did we get this from the same formula that sigma from iota, sorry, I is equals to 1 to n 8 ai into exponential minus bit. From this same formula we got this one.
Okay, can you repeat? Can you repeat the question? So you are asking about with for the spring mass system, right?
Yes, sir. Spring mass system.
And I said in the video lecture that this is not a stable system, right?
Yes, sir.
Okay.
It is unstable system, yeah.
Okay. So this is unstable system. Now you are saying how you are. So what did you say? A1 B1. What you are talking about that?
Sir, you said that this is a multi-degree of freedom systems. That's what I'm talking about, sir.
This is not a multi-degree of freedom system. No, this is the 1 degree of freedom system. No.
Okay, sir. They're having a multiple roots. That's what I'm telling.
Yes, it has multiple roots.
Yeah.
Yes.
Yeah.
There will be two roots.
So in there we use that formula, na, sigma ai into epsilon to the power minus bit.
Just a minute. What equation? Sigma ai.
Sigma, sir. Sigma summation sigma.
Acha. Huh? AI.
Yes, sir.
Okay. ठीक है AI over S plus AI. That you are saying?
Yes, sir.
Acha. Oh, okay. Yeah. Well, this will not come from that actually. This can also come from that also. But here AI is the real number. So that is different thing. But it is same as this one only. They say not different. Basically, not very different. So what? So basically, mx double dot plus kx equal to in that case will be some ft, right? So spring and mass system mk, right? And then this is what the equation is. And then finally, what you get? This you get fs, and here get ms square plus k, and here xs, right? And then you get xs over fs equal to 1 over ms square plus k. You can write that way also. Yeah. So what you will do in that case? It will be 1 over m s square plus k over m equal to 1 over m s plus here omega n square, where omega n equal to root k over m, right? So and s square, where it will be 1 over m and s plus I omega n and s minus I omega n. You can also write this way also, and you can get like that. It's possible. However, since why we write this one? We write this way because this is going, when you take inverse Laplace transform, then you get a value. But in this case, then you say s square plus omega n square, and you are going to write this way, then there will be imaginary number coming on. But from here, so basically there are two way of solving it, right? So if you want to solve it, you will get just sine omega, right? So what you get, if you have in this case fs equal to unity for what? Impulse, right? So in that case, xs will be simply 1 over m s square plus omega n square, and hence xt will be simply 1m, and this one you get over omega n over s square plus omega n square, inverse Laplace transform of that, you get 1 over m omega n. Inverse Laplace transform of this gives you sine, right? Sine omega n t. So what you can see the stability of two way. You can actually find out xt also, and from there you will see that this is a function of time and this is a sinusoidal function. That means once one impulse hits it, after that it start oscillating, right? It start oscillating and goes like this. So it goes like this one, right? And it will never stop. That means it's not stable. The other way is just look at the root only. So you know s square plus omega n square equal to 0, and root will be s equal to plus minus root I omega n. Hence, when you plot on s, the complex is plane. This is positive, this is negative. What you get? 1 you get here, omega n. Here you get this is I omega n. This is I minus I omega n, right? So since this is on this axis also, this is also known as basically the marginally stable, but it's not applicable to all systems. So far in my lecture I said it's unstable, and you have to assume unstable, unless somehow for system it is allowed. Otherwise it is unstable only. So I said unstable because the root is plus minus I omega n. For stability, we need left side, any point at the left side, even not any point. Sometimes you have restriction on the region also. You don't want in this region. This region is not allowed. Only this region is allowed. So you can also do that. But for you, so far, we are just talking about on this axis, it should not be there. Right of this should not be there. Otherwise, it's stable. So many ways of seeing the same thing. Right? Either you can go to t domain, see whether with as t tends to infinity, whether the xt tends to 0 or not. For what? For a impulse, for unit impulse, right? So then you call this a stable. Otherwise, it's not a stable. Did I answer your question?
Yes, sir.
Okay. Any other question, guys? Any other question? No? Okay. The questions, 12 questions are actually the not difficult one. And here, whatever the questions I gave you, if you do, like we have already covered in the lectures. However, the last few questions we will answer later. So later, all these questions, for example, question number 526, 524, 523. No, 523 you can do now. For 24, for that we need further information. 521 and 520. Yeah, so many these questions, please wait, right? Based on mostly based on route and more full route stability. So that we will cover. Yeah. Uh, for 26, we will also need the steady state error, faster way, steady state error. Okay, so faster method that to cover. All other questions we have to you can solve based on the all the lectures that we had. Yeah. Okay, so I'm going to quickly go through all these questions. Yeah, so just to in case you face problem later on. So B51, so it tells it requires 98%. So 1 minute and they say 98%. Yeah, of response to unit step. So when you have unit step, then it reaches 98% in 1 minute. Assuming the thermometer to be first order system, find the time constant. So time constant equal to 1. So you can write the first order system to begin with. So you can say Ts is equal to A over, you can write like that, S plus tau, right? So you can write like that. Okay, so the time constant will be based on that, right? So here the this is nothing but equal to Rs. So you have a system, and this is a reference, this is output. So you have Cs over Rs, right, like that. And any system, first order system, you can write like this one, right? Now this is a step input, right? So Rs is equal to 1 over S because it's a step input. Yeah. So hence you get Cs equal to 1 over S and A S plus tau, right? Okay. Okay, so far so good. Okay, and then will be equal to you can get from here. Let's say this A is okay. So we are going to find out Ct, and for that Ct and Ct will be equal to your let's say call it alpha S plus beta S plus tau, and hence you get alpha S plus tau plus beta S over S plus tau, and hence you can find out based on that you have alpha plus beta S plus alpha tau, right, over S plus tau, right, and hence in this case you have A equal to, so in alpha plus beta equal to 0, and then you have alpha times tau equal to A, and get alpha A over tau, and beta equal to minus alpha equal to minus A over tau. So typically you start like this one. So Cs equal to alpha A over tau. Okay, so A over tau 1 over S plus, and then you have beta, that's a minus alpha minus A over tau and 1 S plus, like that. So you have like this, and then so beta equal to minus A over 2, you have also the just like that only. Yeah. Okay, then CT equal to L inverse CS, and what you get, A over tau, and this one is equal to okay. So the A over tau, and this is equal to 1 only, minus A over tau, and this one is equal to e to the power of minus tau t. Yeah. Okay. Okay. So from here, what you get is A over tau 1 minus E minus tau over t. So I'm taking long way of doing it, but that way you will understand. Basically, this is you can also derive wherever you want. So this is how it is. So the time t is equal to 1 over will be here, right? So equal to A over, so this is time constant. So time constant equal to over 1 over tau. That's what it is saying. So now it says that you have the 90%, 98% in 1 minute. So you can assume t in minute. Okay, t in minute, and then your value CT is 98% of what? When t tends to infinity, then this value will be 0, and CT will be equal to A over tau, basically. So CT equal to 98% in 1 minute. That really means that 0.98 times A over tau is equal to A over tau 1 minus E minus tau times 1. Yeah. So the value you get is 1 minus E minus tau equal to 0.98. Yeah. So okay, so I'm going to erase here. Okay, so what you get? You get 1 minus e to the power minus tau is equal to 0.98, and that tells you 0.02 equal to e to the power minus tau, and hence ln 0.02 equal to minus tau. Yeah, that's what you get. Yeah, and hence tau is equal to minus ln 0.02. Yes, and 1 over tau is the time constant, right? The time constant. 1 over tau equal to minus 1 over ln 0.02. So this is what the value you get, like this. Okay. So this is the more understanding way of doing it without actually using formula or memorizing it. So you have to proceed this way. Okay. Now the second part of that, when say if the thermometer is placed in bath, the temperature of linearly at the rate of 10 per minute, how much error does the thermometer show? So how to do it? So second part. So So our system is we know CT is given by the not now CT is not relevant. One we worked on this one. This is 3, 5, 1 only, second part now. So far what we know that time constant t equal to 1 over tau, whatever we use right now. So depending on how you use tau, so maybe in the lecture I use 1 over tau s plus 1 rather than s plus tau. So it doesn't matter, you can write anyway. So this is t equal to 1 over tau dash we know minus 1 logarithmic the natural log of 0.02. So this is 1 so far, right? So we know that. Now coming back to the Ts is equal to A over S plus tau. That's what we used. This is the actual first order system. There you don't know what the A is basically, right? So there has to be a constant here and then S plus, this is the better way of writing it, especially when you don't know whether A equal to 1 or not. Yeah. So in the lecture video, probably I used S equal to 1. So all those things not always be 1. So that just for example, but this one is the real first order system. General form will be something like this. Okay. Okay. Now, second part, then what it says RT is equal time t. This is RT, and RT is going like this. Yeah. Okay. And what is the slope? This RT is given by equal to 10 per minute. So 10 per minute. So that is the increasing by that. So linear rate of this. Okay. So 10 per minute. So basically beta t already I've taken as. So this will be already, this will give you per minute unit. So 10t. So this is rising like this. So yeah, so RT is like this one. Hence, this one is equal to R CS over RS. Okay, now from here we get RS equal to 10 1 over S square, and hence here we will write CS so CS equal to RS multiplied by AS plus tau is equal to 10 plus S square times AS plus tau. Yeah. Okay. Now we have to factor it, and for that, the factoring is the one thing that we have to do. So this can be given by alpha plus S, right? Then beta plus S square plus you can say delta over S plus tau. So you can write like that. Yeah. So let us see how it works. Equal to we rate S square S plus tau. Yeah, and then we have here alpha S plus tau. Yeah, and here we get beta. Okay, so beta S plus tau, and then we get delta S square. Yeah, okay, and here let's look at S square term will be alpha S square and plus delta S square plus S term. So we have alpha times tau plus beta plus constant term. There is no constant term here. Beta into tau. So divided by s square s plus tau. Okay, and here then we have to compare with the original one, and what do we get? We get constant term first of all. So looking at the constant term, so 10a equal to beta times tau, and hence beta equal to 10a over tau. So we get like this. Then we have the beta this term. So we have s tau plus beta equal to 0, and beta equal to this. So beta equal to minus alpha tau. Sorry, alpha we have to find out. So alpha equal to minus beta over tau, and we have minus 10a over tau square. Right, so we get alpha like that. Okay, now delta equal to minus alpha is equal to 10a over tau square. So hence we get here is equal to alpha, which is equal to minus 10a over tau square 1 over s plus beta equal to 10a over tau 1 over s square plus delta is 10a over tau square 1 over s plus tau. So that's what we get. Yeah. So this is what it takes time in basically, and once you have that, we can actually find it faster. We have Ct is equal to L inverse Cs, right? And which is equal to now 10a over tau square 1 over s. So this will be just 1 basically. You have just one value here. Okay, then plus this one is the 10a over tau and times t is the value, and then plus here we get 10a tau square, and then here e to power minus tau t. So this is what we get. Okay, so a steady state error in this case, we have to find a steady state error. So Ct, so our input is 10 over 10t, right? So basically the error Et equal to RT minus Ct, like this. Okay, and which will equal to where are so this is 10t minus, we have all those. Yeah, so we have 10 minus plus 10a over tau square, and right, then we have minus 10a tau t. Okay, that's what we have. So 10t is here minus, so 10. Okay, so it has to be plus here, no? So RT minus CT is like this one. So 10t plus, here we get plus like this, and this will be minus 10 over tau t, and then minus 10a over tau square e to the power minus tau t. So this is what we have. Yeah. Okay, now we have a things here. So we have to actually look at, we have to find out the value of A also. Yeah. So in this case, how to find out the value of A? So either the A value will be given. The time constant in this case is okay, just a minute, guys. So I think A. So A has to be equal to tau. Actually, I think in this question it's assuming A is equal to tau only. So yeah, in this case, the first order system, I think in this basically it's assuming that your system is something like this only. So not A over S over tau. So A over S plus tau. So you take out here, so 1 over, and what you get here is S 1 over A plus tau term here becomes tau over A. So basically in this case, this is assuming to be the unit A equal to tau basically. So this is 1 over, when you say A equal to tau, then you have 1 over tau S plus, and this becomes a 1. Okay. So in this case, in this question, this is assuming that the value of tau and A are the same, because I think this is based on the example it has given. The first order system, it is just writing as Ts equal to 1 over Ts plus 1, where T is the time constant. But here, I think the first order system can have a constant like this also, again, right? But in this case, gain is assumed to be 1. Then only you can solve it, otherwise you cannot solve it. So, okay, so although it does not mention, but we have to mention, otherwise we will not able to find out. So in any case, what will you do? So here, let me erase. So we get the final value, this one. If A is given, fine. If A is not given, we will assume A equal to tau. Yeah, so here I will write assume A equal to tau. Yeah. Why? A is not given, so that's why. So otherwise you can, or maybe first let's find out the steady state error itself. So ET, steady ESS equal to ET time, bit time tends to infinity. That's how we're going to find out, and which is equal to, from here we can find out. So 10 minus 10A over tau t, right, plus 10A over tau square, and limit 10 tends to t tends to infinity, 10A over tau square, and then you have minus 10A over tau square e tau t, where you have limit tau tends to infinity. So this will be 0, but here limit time tends to infinity, 10 minus 10A over tau t, and then you have plus 10A over tau square. Now, if a not equal to tau, a steady state tends to infinity. Yeah. If a is equal to tau, then so these are general. If a equal to tau, a steady state is equal to you get 10 minus 10 a over tau, 10 minus 10 automatically it becomes 0, right, times t. So this becomes 0 plus 10, you have 10 and then you have a equal to tau and this tau square, so 10 over tau. So this will be the answer where tau is given, where tau is equal to this. This is the time constant, or you can write in time constant terms of time constants also. So equal to 10 times t, where t is the time constant. Yeah. Okay, so this is either it can, in this case, I mean, the a has to be what you come to know here. A has to equal to tau in this case. If you don't, then a steady state error will be very large, and hence this either the so that for the ramp input, the steady state error is finite. It is possible only when t equal to tau. That's what you come to know from that. But this is the right way of solving it. First order system will not always be 1 over like a ts plus 1 form. Yeah, so it may be some constant here, but if you use a step input, then steady state error will be 0 even in this case also. But for ramp input, it will not be. Okay. So any question on that? Any confusion? Okay. Okay, time constant 0.256 minute. Okay. Nice. Okay. So time is also up. So unless you have any confusion, so this question especially I solved because I think there may be some confusion on that, how to go about it when as you although we studied, but a real first order system will look like that, and it will behave differently. So any other question, guys? Okay. So if no question, yeah. So we will see you. Yeah, you can ask, man. No problem. Sorry, I mean, you should not take it personally. When I say that you have probably did not see it. Sometimes you see and also you miss it somehow. All those things. It's okay. You can ask any question, man. I think I should not have told probably like that, but so you can ask any question. No problem. I want to.
I didn't mean that. Actually, the videos I seen at night only, so that's why maybe.
Yeah. Okay. So I recommend that you see regularly. So that's I am like it may be that you may have a lot of courses this semester. Yeah. So but you have to give equal time to all. No. So you have to give justice. And this course a little bit different, so you have to give it basically. Things will come even more difficult little bit. Yeah. So if you have any question, any silly question, anything, is okay. I want to encourage. I feel bad when I seem to discourage by some comments on all, so it should not happen. Ayush, what about you? Any clarification, anything? Okay. Okay, guys. Okay, guys. So see you next week then. Okay. Bye.